All right, this is the last video in the series for Unit 7. This is on infinite series. We've already talked a lot about infinite series as we've worked through some of these other problems. In fact, we've seen some of these problems before, and so this is just a formal discussion then of the infinite series. We're going to review one of Zeno's paradoxes. He had more than one. We're going to discuss divergent and convergent series. We're going to find the sum of an infinite series that is convergent. And we're going to write the infinite sum using summation notation and find the sum if it's possible. I really like this cartoon. I think the title on it, which didn't come with the picture, was something like their boyfriend and girlfriend. And so she's applying Zeno's paradox. Anyway, I thought it was kind of funny. Okay, you recall that Zeno's paradox was if you approached a wall, but you could only go half the distance each time to the wall, would you ever reach the wall? And the paradox is that, of course, you would reach the wall. Your nose would eventually hit the wall. But in reality, the infinite slices would mean you would get really, 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 really close to the wall, but you would not actually touch it. So you would just keep doing half the distance, half the distance, half the distance, and never reach it. So we're going to use this idea of an infinite series to see that even though you don't reach the wall, you could actually sum up a series that continuously goes on forever. So there are two types of infinite geometric series, and it lost the S there. One is diverging. And I drew the arrows here because the series keeps getting bigger and bigger and bigger. So we are talking about geometric. So the common ratio would have to be bigger than 1. It doubles, it triples. You multiply each term by 8/3, something. But the R has to be greater than 1. And as it gets bigger and bigger and bigger, there is no way to sum up those numbers. So a divergent geometric series has no sum. However, a converging, and you can see the arrows here, a getting smaller, a converging series, one in which the ratio is somewhere between 0 and 1, and I have the absolute value of R because, of course, the series R could be, it could be a fraction, somewhere between 0 and 1. So these series, as they are getting smaller, you can see here, get smaller and smaller and smaller, starts to actually act like Zeno's paradox, right? You start 4 feet away from a goal, the next time you're 2 feet away, then 1 foot away, then half a foot, then a fourth of a foot, then 1/8, 16th, 32nd, and so on and so forth, until you get so big on the bottom that you're getting very, 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 very close to 1. So you can see here that the sum of an infinite series, and sum, anytime you have sum, you can write it with summation, 0 to infinity of A, right, A sub 1, R to the K, is equal to the first term, A sub 1, times 1 over 1 minus R. So you can actually find the sum of a converging geometric infinite series. So if it were possible to add up all the terms of the geometric sequence that halves each time, so the first term is a half, and then a fourth, and then an 1/8, and then a 16th, because it divides each piece into a half, it would look something like this, okay? So I have a square, this is half, this is what I started with, add to it a fourth, add to it an 1/8, a 16th, a 32nd, a 64th, a 1/28th, a 2/56th, et cetera, et cetera, et cetera. This actual sum is going to approach what? 1 square, right? So if you start with a half and you add a half to it each time, you're going to, if you use the formula, the sum of this infinite series would be the first term divided by 1 minus R, which is 1/2. This is 1/2 divided by 1/2, which is 1, and illustrated here. Now, we've actually seen this before in the summation chapter. We have the sum, this is an infinite, the sum of an infinite series, A sub 1, right? If I put K in, A sub 1 is going to be 0.6. The next term would be well, let me write it this way. 0.6, obviously, but I kind of jumped ahead there. So it's really 6/10, right? And then plus 6/100, and then 6 over 1,000, and then 6 over 10,000, et cetera, et cetera, et cetera, right? So it goes on forever. So this is 0.6 plus 0.06 plus 0.006 plus 0.0006, et cetera, et cetera. And if you add all those together, you have this, right? Which is 2/3. Okay? But if you use the formula, an infinite series, the first term is 6/10. R is 1/10, so 1 minus 1/10. 6/10 over 9/10 is 6/9, which is 2/3. Now, notice that's a 6. 2/3 is 6/9. Now I have 0.33333, and I'm going to write this as a summation and find the sum if it exists. Okay, so I'm going to go from, write the summation, the sum, it is an infinite series because it doesn't change. K equals something to infinity. R is 1/10. Okay, that's my R. And then the first term would be, if I put a 1 in for K, this will be 3/110 to the K. Right? So whenever you make a rule, you need to check it. So if I put a 1 in, I get 3/10. If I put a 2 in, I get 3/100. If I put a 3 in, I get 3/1000, and continuing on and on. If I write that as a decimal, I get the repeating decimal. Okay? So R is 1/10. A sub 1 is 3/10. So the sum is the first term over 1 minus R. This is 3/10 over 9/10, which is 3/9, which is 1/3. So the sum of this infinite function is 1/3. If you take 1 divided by 3, you'll get that repeating decimal. So what would it be if I did 0.4444444 or 0.111111, right? I could write the same rule going from K equals 1 to infinity of 4/110 to the K. And if you'll notice, it's probably going to be 4/9. Why is that? Do you see a pattern? All right, so if we notice here, we notice that this is also a repeating decimal, but it is repeating every 3 places. So the rule for this starts out kind of the same, K equals 0 to infinity of 1, 2, 3, 1 over what? To the K. So this time I have 3 places. For the last time I had 1 place that kept repeating over and over. So if I have 3 places, this is going to be 1,000, right? So this is 123 over 1,000, 1 minus 1 over 1,000. So this is 123 over 1,000 divided by 999 over 1,000. When you divide that out, right, you end up with 123 over 999. So that's an interesting repeating decimal. So what if you had 0.23232323, right? That would be 23 over 100 divided by 1 minus 1 over 100. So that's going to be 23 over 100. I'm not skipping any steps. 99 over 100. Are you seeing the pattern? 23 over 99. And if you don't believe me, throw it in your calculator. You'll get that repeating decimal. Now, I want you to look at the summation that I wrote and see if you can figure out why it's incorrect. And I'll see you in class. All right, so for your homework, after you've watched this video, I want you to work these 3 problems. Find the sum of the infinite series if it exists, down here. Write the summation and find the sum of this. So on these, you just need to use the formula. This one, I want you to actually write the rule. See if you can do that with what you wrote in the notes. Some of you are still a little shaky on summation. This gives you another opportunity to practice. All right, that's it, and I will see you in class.